this right angle triangle. And with immense gratitude to the great mathematician Pythagoras, we are going to use his theorem. Well, Pythagoras' theorem said the square of hypotenuse is equal to sum of square of other two sides. What did he say? He said the sum of square of other two sides means AB squared plus BC squared is equal to AC squared. Thank you, Pythagoras. Pythagoras. Now, once we get this Pythagoras equation, just for fun, we are going to divide this equation by AC squared. All right. So we're dividing both sides by, I said just for fun. Okay. So dividing both sides by AC squared. Okay, one moment, by AC squared. What do we get? Look, AB over AC squared. AB squared over AC squared is equal to BC. Oh, it's plus. We have plus BC squared divided by AC squared is equal to AC squared over AC squared. Can we say, I mean, both the numerator and denominator are squared. Can we write them together? I mean, AB over AC whole square like this. Plus, then this, the second term can be written as BC by AC whole square is equal to AC square is 1. What is the value of AB by AC for, say, any angle we can consider? Let's consider this angle A. All right, let's say this angle A is theta. Measurement of this angle A is theta. Now, this is the theta is a Greek letter that we use just like alphabet X, Y, Z, A, B, C in English. We use theta in Greek. So AB by AC would be, where is AB? AB is this side, which is adjacent to the given angle. So this side is adjacent side because it is part of that angle which we are talking. And then angle opposite to theta, this is side opposite to a given angle theta is here. And now we want to define AB by AC. By definition, AB by AC was adjacent by hypotenuse, which was cos theta. So we can say cos theta square plus BC by AC. Similarly, BC is the opposite side, AC is hypotenuse. So that was sine theta. You know, the ratio of these two sides is sine theta, and the square of this is equal to 1. For convenience, we would not like to write this bracket every time we square any trigonometric function. So what did we do is, instead of writing it like this, we would simply write the square in between theta and cos. So cos square theta. Now I don't need to put this bracket here. Plus sine square theta. Cos square theta plus sine square theta is equal to 1. So this is one of most profound trigonometric equation, actually trigonometric identity, because it will be true for all values of theta. Look, this theta can be made smaller and bigger by shifting this A to the closer. Look, it's the theta might get almost 90 if we shift this A very close to B, and at when A comes in the place of B, then it is 90 degree. Similarly, theta can be made bigger and bigger. How? The one way of making theta bigger is like this. Oh, look, what we can do is, okay, this theta was actually getting 90 degree when we take it close to that here. This theta bigger, 90. That angle is getting 0. And What we mean to say is now the identity that we have derived right here, cos square theta plus sin square theta equal to 1, will be true for all values of theta. And what this theta can be? Theta is an angle of a triangle, right angle triangle. So this angle can be between 0 and 0 is less than theta is less than equal to 90. In this case, when we are proving our identity using a right angle triangle, we know our theta is between 0 and 90. So the identity written down there, cos square theta plus sin square theta equal to 1 is true for all values of theta between 0 and 90. Actually, we would be in this topic discussing angles between 0 and 90 only. So the first identity that we derived is with the help of Pythagoras theorem is sin square theta plus cos square theta is equal to 1. We derive sin square theta plus cos square theta equal to 1. This identity can be written in a couple of more ways, like we can actually write sin square theta is equal to 1 minus cos square theta. Can we? We can also write cos square theta. We can take the sin square theta to the right hand side. So we can write cos square theta is equal to 1 minus sin square theta. And taking square root on both sides, square root of sin square theta would be sin theta. Sin theta can be written as take square root on the right side, 1 minus cos square theta. We can write like this. And the second identity, I mean, the same identity, but the second form of this identity can also be written as cos theta is equal to square root of 1 minus sin square theta. Is it done? Perfect. The other one, we just have proved one of the identity. We were playing with Pythagoras theorem. We divided it by something. Let us again do A, B, C, and the Pythagoras theorem was AB squared plus BC square is equal to AC square. Now we can also divide. There are three sides. No, we divide it by AC square. What if we divide it by AB square? So divided by AB square, divided by AB square, divided by AB square, divided by AB square. What do we get? Look, AB square by AB square. The first term becomes 1 plus BC by AB means BC is for angle, let's say this is theta. Any of the angle we can take theta, the angle. Then BC would be adjacent. So the side attached with theta would be adjacent and this would be opposite. So do not make any mistake in identifying sine and cos. I mean, in identifying opposite and adjacent side. And once you identify opposite and adjacent, you can always use SOHCAHTOA to find to define these trigonometric ratios sine, cos, and tan. Okay, now BC by AB, as per that, BC is adjacent by BC by AB. Is that cot theta? Reciprocal of 10. 1 plus cot is cot BC by AB whole square. Can we write one more step and then define it? 1 plus BC by AB whole square is equal to AC by AB whole square. All right, so 1 plus BC by AB means cot theta square, AC by AB, hypotenuse by opposite, that is the reciprocal of sine, which is cosec theta square. So can we rewrite this? I mean, removing this bracket, can we rewrite this 1 plus cot square theta? 1 plus cot square theta is equal to cosec square theta. So this is the another identity, trigonometric identity. 1 plus cot square theta is equal to cosec square theta. Just like this one, We can also divide like the third side, you know, we divided by AB. Can now we divide by BC? Okay, we can do that as well. Let's see what kind of identity we get. Now divide both sides by BC square. What is going to happen? Divide and see for yourself. So you divide both sides by BC square, you get BC square by BC square, you get AC by BC square. Perfect. Now BC by BC would be 1, whereas AB by BC, look at this. AB divided by BC. What is AB by BC? AB is the opposite side and BC is the adjacent side. Opposite by adjacent, the square of this, plus BC by BC is 1, is equal to AC by BC would be hypotenuse by adjacent. That is reciprocal of cos, which is also known as sec. But first we will write AC by BC and we will say square of this. All right, so AB by BC can be written as AB by BC is 10. 10 of theta whole square plus 1 is equal to AC by BC would be AC is hypotenuse by BC, that is sec adjacent side, you know, sec theta is squared. That means, well, now simply we'll remove the brackets. Unnecessary, we say now, the luggage, drop it. This is 1 plus 10 square x, or 10 square x plus 1. 1 plus 10 square theta is equal to sec square theta. So these three trigonometric identities we can get just out of Pythagoras theorem in a right angle triangle. This triangle up here is a right angle triangle. So three identities, even these other two identities can also be written in two different ways. Like if we have the identity 1 plus 10 square x is equal to sec square x, x is the angle in place of theta, then we can write 1 is equal to sec square x minus 10 square x, right? Or we can transport this 1 to the right, or we can say 10 square x is same as sec square x minus 1. So the same equation can be written in three different ways. Finally, using Pythagoras theorem, we have got three trigonometric identities. The first one is sine square theta plus cos square theta equal to 1. Second one, 1 plus 10 square theta is equal to sec square theta. And the third one is 1 plus cot square theta is equal to cosec square theta. Now, these trigonometric identities helps us to find other trigonometric ratios when any one of these trigonometric ratios is given. Now, how can we do it without actually drawing that right angle triangle the way we used to do earlier? We can actually use these trigonometric identities and straight away find the value of other trigonometric ratios. Let's see here one question. If sine A is 1 by 2, determine the value of other trigonometric ratios of angle A. So we are given sine A is equal to 1 by 2, and we are going to use that trigonometric identity sine square A plus cos square A is equal to sine square A plus cos square A is equal to 1. What is the value of sine A? 1 by 2. So this will imply 1 by 2 squared plus cos square A should be 1. This implies square of 1 by 2 is 1 by 4 plus cos square A is equal to 1. So cos square A would be 1 minus 1 by 4. This is 3 by 4. So if cos square A is 3 by 4, then cos A would be square root of 3 by 4. Now square root of 3 is square, we'll write as it is, but the square root of 4 is 2. So we get the value of cos A. Now we have sin A, we got the value of cos A. Remember one more trigonometric formula, like tan of A, tan of any angle can be written as sine of A divided by cos of A. Why we can write it? We have given proof of this in one of the previous video. You can go and see it there. And for this question, you can directly apply tan A sine A over cos A. So we get the value of tan A now, sine A cos A. So what is the value of, now if we need to find tan A in this case would be sine A divided by cos A. What is the value of sine A? Sine A divided by cos A. And we know the value of sine A was given, which is 1 over 2. So the value is 1 over 2 divided by cos A is square root 3 over 2. Now this value can be written as 1 by 2 multiplied 2 by square root 3. Division of the fraction, we reciprocate the denominator. That is the common way of doing it. 1 by square root 3 is the value of tan A. Now we were given sine A, we got cos A, we have also got tan A. Now the other trigonometric ratio, which are the reciprocal of these trigonometric ratios, could be easily found. Like you can say if sine A is given, you can directly say cosec of A. Cosec of A, which is the reciprocal of sine. 1 over sine A, that should be the reciprocal of 1 by 2, which is 2. The another trigonometric ratio is sec A, which is the reciprocal of cos. 1 over cos A, that should be the upside down of this value here. So your sec A value should be 2 by root 3. And finally, the last trigonometric ratio, which is cot of A, is 1 over tan of A, and tan of A was 1 by square root 3 over here. So the reciprocal of this would be square root 3. So this is easier way to find other trigonometric ratios if one of the trigonometric ratio is given, simply using these trigonometric identities. 3 of them we have done. One is written right here. Sine square, one is used in this question. Sine square A plus cos square A is equal to 1. You can use whichever is applicable in a question, in a particular question, as per the given things or given trigonometric ratio. Right, I think it made some sense. So this will be true, this trigonometric identity, which will be true for all values of A, and we can use it when sine A is given to find all other trigonometric ratio, as we did in this case. Now let's take one more question, then we wind up. Express all other trigonometric ratios in terms of sine A. Look, you are given sine A here, you are asked express all other trigonometric ratios in terms of sine A. Now the identity sine A plus cos A, we already know, like cos square A plus sine square A is equal to 1. So what we are going to do is cos square A is equal to 1 minus sine square A. That means our cos A would be square root of 1 minus sine square A. Well, we have expressed cos in terms of sine. Now we can also express tan in terms of sine. Okay, what would be tan A? A moment back, we saw the tan is the tan theta can be written as sine theta by cos theta. So tan A can be written as sine of A divided by cos of A, and sine A will remain as it is because we want to express this in term of sine, and the cos A, value of cos A in term of sine is given up here, which is under root 1 minus sine square A. Well, tan A is also expressed in term of sine A. Cos A has been expressed. Other trigonometric ratios which are reciprocal could be expressed in term of sine A. Like cosec A can be said as, cosec A would be reciprocal of sine. So you can say 1 over sine A. Look, even cosec A is being expressed in terms of sine A. Now, the next one is tan A, and the reciprocal, the cos A is known, and the reciprocal of cos A is sec A. So we can express sec A also in term of, that is 1 by cos A. But we want to write this in term of sine. So that would be 1 by, the value of cos A is 1 minus sine square A. And finally, we have cot A. Cot A is the reciprocal of tan A. So cot A can be written as this value upside down. Okay, that means cot A would be, cot of A would be a square root of 1 minus sine square A divided by 1 divided by sine of A.